My name is Laura Gomez-Rey, and this is my Physics 2212 Lab 5 on magnetic braking with Faraday. So introduction for this lab, the overall purpose is going to be to collect data from your life and computationally understand Faraday's law. And some overall results is that in real life, experiment that I did, it was 0.86 seconds for the magnet to fall down from the aluminum tube, and then computational it was 1.189 seconds using glow script. And then for the system was the aluminum tube and magnet, and the surroundings was everything else around. So some main concepts that we're going to need are Faraday's law, so we can calculate the current induced in each ring by the falling magnet, as shown on the right. And then we're going to also need the Biot-Savart law, which we're going to need to calculate the force exerted on each current carrying ring by the falling magnet, also shown on the right. And then Ohm's law, we're going to need this to calculate the induced current, which is just V is equal to I times R. And then we're also going to need Newton's third law to calculate the force exerted on the falling magnet of the whole tube, and Newton's second law for the position and velocity updates in the glow script code. Alright, so for the real-life experiment, our initial conditions were that the length of the tube was 0.31 meters, the inner diameter was 0.0025 meters, and the width was 0.006 meters. Total width was 0.031 meters, and the steps were that I dropped the bar magnet down an aluminum tube and then recorded the time from the top to the bottom, how long it took the magnet to get from the top of the tube to the bottom of the tube, and then I repeated that 5 times with, as shown on the right, the average time being 0.85 seconds for the magnet to get all the way down the tube. And then for the glow script code, we pretty much did the same experiment, but now on computational, so probably less source of errors, because in real life there could be some gravity errors or air resistant errors. So here in the first screenshot we have the initial conditions of the tube, then we have the magnetic field function, and then also the magnetic flux function that we need to find the current and how long everything's gonna, how long the magnet's gonna take to get down. And then here in glow script 2, we see the induced current, so basically the equation that I used to find the induced current, and then we see that we needed the flux, and then I also calculated for the magnetic force calculations, and then the net force calculation is just going to be F gravity plus the F magnetic to find F net. And the results for the glow script were that it was about 1.2 seconds for the magnet to fall from the top of the loop, the top of the tube all the way to the bottom of the tube. And here on the right you just see the magnet, which is the blue is the north, the S is the south. You just see it falling down. Okay, so for the computational analysis, which color corresponds to clockwise current, which counterclockwise, and how can I know? So I can tell that counterclockwise is going to be blue and counterclockwise is going to be red, due to Lenz's law. And then what happens to the dynamics of the system when you flip the magnet around? We're still going to have the same results. Nothing's going to change at all. Same thing's going to happen. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? For the gravitational force is greater at the end of the tube, but while the magnet is in the tube, the gravitational and magnetic force are equal. And compare the tube and the computational and real-life experiment. How does the total time in tube of the real-world system compare to the computational system, and how might the computational system be more accurate? Both of them were actually already pretty comparable, and it could be made more accurate by just adding more rings to the simulation, or just by simply recalculating the magnetic dipole moment. And for discussion, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? it would basically, the induced current would be much larger and the magnet would take even more time to fall down the tube. And what if holes or slots were cut into the tube? How would this affect the rings of the model? The tube would have less rings, so it would actually do the opposite of the previous question. There would be less magnetic force, so the time for the magnet to fall would actually decrease instead of increase. And that's it. Thank you.